Oh,
All right, so welcome back, and all right, so you can see my slides, right? Okay. So remember, last day we stopped at the definition of exponential. So exponential is nothing but this power series, and we essentially proved that this is defined all over C. Another notation, which is also very popular and common, is x, exp at z, which is also written as e power z. So one more time, this is just a notation. You can consider this as a function, notation of function, okay? So like exponentials, if you look at this sum, z power n over n factorial, sum n to 0 to infinity. By the way, I'll go a little faster today because I think the major part has been explained, and some other small details I'll do, and then I move on to the next part. So when you look at this sum, you collect all the even terms and multiply with minus 1 raised n. That's the definition of your cosine z. Look at this carefully. This is again a power series, and it's going the radius of convergence, that Lim-Sup formula what we learned yesterday, or even an plus 1 over n, that limit formula. Priyanka, you have some question? Please go ahead.
No, sir, it was by mistake. Sorry.
Okay, no problem. So you look at this. So this is going to be also a power series and going to be defined all over C. You agree, right? I mean, this is just this series with plus minus, but you take modulus, it disappears, right? So are you convinced now that cosine or sine? So similarly, you define sine z with the odd terms and again with minus 1 raised n as the coefficient part, okay? So these guys are also defined all over C. So now you understand that exponential, cosine, sine, how they come. And when you, okay, so this is what I said. The right hand side of one is power series with radius of convergence infinity. I said y, but you can compute this with your formula. And this is the definition of your cosine, and similarly sine. Similarly, this right hand side of 2 is the right hand side. Okay, so this is the same sentence I just left as a dot. Okay, all right. Now you do this, but with a purpose in mind. You actually write e power iz. So you look at the definition of ez and or exponential of z, and then you write exponential of iz. So if you write z as iz, then something will happen here, and whatever happens is your nothing but cosine z plus I times sine z. This is how you actually introduce cosine and sine. Okay, so this is going to be again sum of two power series, and it converges perfectly since it's defined everywhere. Okay, so with this formula, which is very well known to you, you define, you get. So if this is the case, then you get e power minus I z, you write, and you get sine z as 1/2 times I. E power iz minus e power minus iz, and similarly cosine z as sum of these two. Here plus iz, here minus iz, and these three formulas, let's call these three all together, is known as Euler formula, and you are very much familiar with it, and this is usually how it comes. Okay, stop me if you have any question. You don't have to raise hand because sometimes I don't see who is doing what. Okay. All right, so now, so we understand exponential, sine, cosine, and let's get into the definition of differentiability. So you have just like the real case, you have a function from u to c, u is a subset of c, and a is an interior point, just like one variable, if defined, f is differentiable at a, if this limit like a real variable, which you are going to call f prime a, if it exists at all. If this exists, then you call it is differential, right? And of course, since perhaps you are tuned with complex analysis, this is the derivative, the notion of differentiability, or in the sense of complex functions, or what you call as holomorphic function, right? So you do that, and there is another powerful result, or what I say, the idea of power series also gives you the term by term derivative. So if you look at this power series, for instance, now look at the right hand side. Consider these as a polynomial. Let's say this terminates. It's not infinite. Then you can do the term by term derivative, right? The power series tells you can do the same thing in general, provided you stay on the same inside the same region. In other words, if you have given a power series, then you know this is defined on the region of convergence right here. Now you do what? You define term by term derivative of this guy and call capital Fz. Okay, capital Fz is this term by term derivative, which is also power series, and the same result gives you region of convergence where this is defined. The power of this result is the following. So given this, you cook up this, nobody stops you. The result says, in this case, this radius of convergence and that radius of convergence will be same, number one. And number two, the derivative of these guys. So the differentiability is assured, and the derivative of this guy is going to be the term by term derivative. So you understand the heart of the theorem, right? A power series you take, it's like polynomials. You can differentiate term by term. You get a new power series. The idea is that the new radius of convergence will be equal to the old radius of convergence. That is this part, and the derivative is going to be the term by term derivative. Is it clear? And proof, trust me, it's just simple binomial theorem, even if it is a page long, but it's just simple binomial theorem. I recommend you to do that. And once you agree, then you look at the exponential function, which is defined all over C. So it's the R is infinity here. And you do the term by term derivative. If you look at the definition here, so if you do the term by term derivative and if you add it up, you get back again e power z, right? So what is the derivative of z power n? It will be n times z power n minus 1 and it cancel out. So z power n over n minus 1 factorial, right? So that's the fun thing. And I told you yesterday, this is really very, very strong property. Okay. So exponential is its own derivative. And this is really, really an impressive property, which was observed not in the complex case perhaps, but in the real case perhaps by Euler. I don't know that part, but during that time. Okay. So I call it an impressive property, and then I say some more impressive properties. And here I go a little faster because not so hard, perhaps. Okay, but I'll tell you the key ideas, and that's very important. I'll give you the key ideas, then it's your job to work them out. Okay. First property is that it's very interesting and important. You see, what happens often we overlook because we take it granted, but these are not. You need details. Okay, so that's what I'm trying to say. Exponential z times exponential w is exponential z plus w for all zw in C. Okay, if you try to do this, you should feel some problem, and the problem is the following. Suppose this is a general problem. Okay, suppose you have a pair of series alpha n and beta n sum, where alpha and beta n in C. Sequence of complex numbers, series of complex numbers. Okay, the Cauchy product. See, if you take a pair of polynomials, you take the product, you know how the coefficient look like, right? So you exactly mimic the same thing and take simply the product of these two. Okay, so if you take the product, you will get a new series. You don't ask the convergence yet. We'll talk about this later. And how this product is defined? Just the standard multiplication. So first term, second term, etc., nth term will be sum of alpha n minus k times beta k from 0 to n. You agree? I think this case is also included, but I have written, I don't know why. I mean, this is already included in any, you can say n equals to 0 also. Is the definition part is clear? Just the product, standard product. Okay. But when you ask, am I going to get this product? Am I going to get alpha n, sum of alpha n times sum of beta n equals to sum of gamma n? That should be the ideal situation. Do you understand? You take a pair of series, take the product, and you look at this product, what I call Cauchy product, and you expect them to be equal. In general, it is not true. You need some assumption, and that's the fun. So the assumption is the following. Suppose alpha n and beta n both are absolutely convergent if they are both absolutely convergent, then the product is also absolutely convergent. I think both absolute convergence, both of them absolutely convergent is not really needed. One of them is convergent, another is absolute convergent. So we can also do that. But for our purpose, since there's some noise, I guess. Since we are interested in exponential of z, this is absolutely convergent. So please, I think, for our purpose, you can just stick on absolutely convergent. Okay. So once you agree that both of them are absolutely convergent, then the Cauchy product will converge and will become equal. Then the proof is just straightforward, because you write Ez times EW as gamma n, where gamma n by this Cauchy product formula is this. This is just a simple binomial formula. You just pull out the n factorial. You kind of balance. So if you write 1 over n factorial here and n factorial there, you are going to get n choose k, which is nothing but 1 over n factorial c plus w raised n. That gives you the proof. Okay, so do this little detail and this homework. I don't know whether this will be done in the tutorial, but you should try to do it by yourself. It's not hard at all. It's a very interesting homework. Please try to do that. And very useful. Now, few properties. E power 0 is 1. Yes, trivial, right? Remember the definition. So 1 plus z over 1 factorial and so on. Now, e power z is never 0. Well, it follows from here itself, because e power 0 is 1, which is e power z times e power minus z. I'm using the previous formula. Okay, this formula right here. And that tells you e power z cannot be 0, right? And here is an interesting and useful property. So denote by x the real variable. So you can, from the, if we talked about exponential as a function of z, but from there you can also consider exponential as a function of x, right? How you do that? X will be, x will be denoted, x will refer to the real variable. So you write e power x as e power x plus I. Nobody can stop you, and in that case, you just say you get your real variable exponential function. Okay. Now these three properties actually help you to draw, if you wish, the graph of the exponential function. So along with this property, e0 is 1 and so on and so forth, or e1 is 2.7. Right? All those things helps you to draw the graph. So first property is e power x is monotonically increasing positive function. Again, x is real variable. Second is e power x converges to infinity. Okay, e power x converges to infinity as x goes to infinity, and e power x goes to 0 as x goes to minus infinity. Okay. And this is the graph. It's a bit curious. So this is the graph of e power x. I'm not going to go to the ln x, but as you know, it's the kind of inverse, right? And this is the graph of ln x. And it's very easy to remember if you do it in this way, is it not? Because e power 0 is 1, e1 is 2.7, etc. You know what is e power 1, right? This is 1 plus 1 over 1 factorial plus 1 over 2 factorial, etc. That was Euler's answer, and he actually came up with the answer as 2 point. If you add few terms, that's how it will come out. Okay. And I leave the proof. It's very easy. Just write the value of e power x and do those computations. I leave it to you. It's not hard at all. And then number 4 is that e power x is 1 if and only if x equals to 0. Well, we know x equals to 0 gives you e power, x equals to 0 gives you 1 by definition. You don't consider this some number or, well, yeah, it's like that, of course. But what about saying that e power x equals to 1 gives x equals to 0? So here is the argument. E power x is strictly increasing and e power 0 is 1. So there is only one way to get it, which is 0, right? Correct. And so these are the small things you want to have a careful look, okay? Not very deep, but you want to look at it carefully. And I'm sure you know all these things. Fifth property is I have a question for you here. Okay, so I'm saying exponential of z conjugate is exponential of z conjugate. You understand the equality, right? Right. And why it is so? So here is my argument, and you have to tell me whether I'm doing a little bit too much or not. Can you see this straightforward or something? You have to tell me. So I'm saying modulus of z bar equals to modulus of z. We know the conjugate is preserved under modulus. And then I'm saying, see, what is the definition of e power z? It's like you can say that Sn converges to the function that's e power z, right? Sn is what? The nth partial sum of the series. If it converges to e power z, then by continuity, Sn bar will also converge to Ez bar. Continuity of what? Continuity of modulus. Okay. So if this goes to this, then this bar also goes to this bar. Oh, continuity of the conjugation. So I'm using the continuity of the conjugation. So you have to tell me, if not today, maybe next day, whether I'm doing too much or not, whether you see it straight away or not. Okay. So that's one. Sn bar converges to Ez bar. But now I say Sn bar also converges to Ez bar over here. Why? Because Sn is a polynomial. So if you look at Sn bar, you know, those bar will go inside, and you are going to get these as the partial sum of z bar power n over n factorial. Okay, so if this two happens, then this must be equals to this, and that's my argument.
Excuse me, sir.
Yeah.
Sir, why can we use the Euler formula here to prove this?
Euler formula. That's a where is that? Where is that, by the way? Did it right? Where is that? Right here. What is Euler formula? This one? Why it is so? Why it is so? Can you tell me how I get it?
Okay, that's IZ. No.
No, right? But using that, you can do several things. In somewhere, you have to do that. Okay? But you cannot. Any other question? No other question? Okay. So just for curiosity, it's not completely trivial. You have to do a few lines. So please do it and try to understand why I'm doing this. And one more time, am I doing right? Am I doing too much, or can you do it very quickly? Okay. Sixth property. Let's say that t goes to e power it maps the real line to the circle, and it's very easy. Leaving to you. And fourth one is, so you look at the Euler formula, e power iz equals to cosine z plus I sine z. And if you focus on the real line, now I'm back to t. I do not know. Maybe I was copying from Rudin, maybe. So never mind. I mean, it's very clear. So I say that t belongs to R. So e power it equals to cosine t plus I sine t, and that's I think you know what you know as Euler's identity. It follows from there. Again, since sine z cosine z is a power series, and the way we cooked it up, if you look at it very carefully, then the term by term derivative of sine z will give you cosine z, and similarly cosine z's derivative will give you minus sine z. So this is how they come. Okay, these are the reasons. And number 9 is a bit of interesting computation, but I have done quite carefully, although copied from Rudin. I have said that. If you consider cosine x, then cosine x is 1 minus all these even powers, but with alternate sign. That will tell you if your x is 0, then cosine 0 is 1. And here is some argument, easy argument, which you should do, which you should look at. And then you find out cosine 2 is less than minus 1 over 3. It's a bit cleverly done. So please have a look. I've given a clear reason. Also Rudin has given same thing, but I think I have done a 1 or 2 more line extra. Okay. So look at this block and look at this block. What you are saying, at 0 it is 1, and at 2 it is minus 1 over 3. Now you know x goes to cosine x is continuous. It's differentiable, not only continuous, it's differentiable. And this happens, then you can assure that at some point that cosine is going to hit the point 0. Okay, cosine is going to get, there will be a point x0 which will be in between 0 and 2, and there may be more, but you can take the smallest one, such that cosine of x0 is 0. Perfect. And that's the definition of your pi. So pi is that x0, 2 times of that x0. So that's how you define your pi. So what is pi? Pi is 2x0. And what is x0? X0 is the smallest positive number in between 0 and 2, such that cosine x0 equals to 0. That gives you the avenue to define pi. Okay, it's very, very interesting. So in other words, x0 is pi over 2. And if you agree with that, your cosine pi over 2 is 0. Very, very nice. And then you use the formula sine square plus cosine square 1 to get that sine 0 is also 0. Sine 0 is 0. And with a little more work, you get sine 0 is 0. It's very trivial. You don't have to do all this. You have to use this, I guess, to get sine pi over 2 equals to 1. Once you know sine pi over 2 is 1 and cosine pi over 2 is 1, then you hit the Euler's formula. And from there, you find e power I pi by 2 equals to I, complex I. And change the side. It's familiar to you. Change the side. You get e power I pi plus 1 equals to 0. And I call it a remarkable equality. And then I say all in one. Can you tell me why I said that? Or is there any good reason to say that? Can you tell me quickly why?
Here we consider all types of numbers.
All types of
numbers, like here 1 is natural number, pi is irrational number, I is complex number, is transcendental number.
That's right. So it is like that. And this is also an incidence where pi is a kind of a geometric number. Don't you agree? So it's kind essentially comes from geometry, right? Exponential is not. Exponential essentially came from the real life problem, but it's not. Doesn't have anything to do with geometry directly. I is the complex, square root of -1, and 1 and 0 is also they're also your favorite number. So this is all comes in one formula, and that's why I call it remarkable equality. Okay. From here, you can go a little very easily. You can prove that e power z plus 2 pi I n is e power z. Very easy. From here, you can take the sum powers and all that. And at this level, I leave it to you. So you are all set to prove the following. And I said it's the routine. And this is the last tiny part of routine, first, second or third page. For you have to look at the details if you don't get it, but I'm sure you are going to get it. Try yourself. If you can't, look at routine. It's mere computation, nothing else. What are those? Number A. So this is part A. It says pi is the unique positive number such that e power pi I over 2 is I. Is it right? Okay, yeah, right here. And such that e power, if you get e power z equals to 1, then the z over 2 pi I must be an integer. So there's another way to say that. Another way to say this is that z equals to 2 pi I n for some n. Okay, so e power z equals to 1 if and only this happens. That's what it says. Okay, and you know this, but finish the little gap. There is not much left. Part B, exponential is 2 pi periodic. It's already kind of here, but you have to show that 2 pi is the least period here. Okay, so please do that. Not hard at all. And part C tells you that t goes to e power it. We consider that as map from R to T. it's not only a simple map, it's also an onto map. It's not a general map, it's just onto, also an onto map. Okay. And finally, the exponential map from C, we know that it's all divided all over C, to the punctured plane C minus 0 is onto. I am sure you know this, but have a look, and if you can't, just look at the reading, the last part of this second or third page. It's not much. So this is all I wanted to tell you about this exponential function, and if you have any question, please let me know. And if you feel I have done a little fast, but not really. These are not hard at all. I have introduced all the key part, okay, and then it should be your part also to do as homework. Any question? All right. If you don't, then I switch to the set 2. So this is set 2. Can you see a new slide?
Yes, yes, sir.
Fantastic. All right. So here is I'm going to talk about more measure theory, and so first of all, this is known as the extended real line. This is known as extended real line. What is this? Well, it's nothing but your real line union with two symbols plus and minus, which popularly is which is popularly known as plus minus infinity. Okay, but treat them as symbol. And while you do that, you also introduce some standard ordering. What is that? Well, you say that any real number is in between minus infinity to plus infinity. So you're talking about kind of ordering here, So this is the ordering I'm talking about. And then you also introduce your arithmetic. So you say infinity plus infinity is going to be infinity. You say that if a is positive, then you multiply infinity with a couple of, okay, with a, then you're going to get infinity. If your a is negative, you're going to get minus infinity, etc. So you use your intuition. All those things should work out in a same fashion. While you extend this real line, now you see my handwriting is so bad, even I cannot read this. I have written something. That's the fear I have for this extended real line. Still bad, but okay. So from this point of view, if you take a subset S, I'll talk about this maybe in the next lecture a little more. So if you take a subset S of this extended real line, you can talk about supremum or the infimum, but in this case, your supremum and infimum is going to exist. So you are going to hit infinity or minus infinity, but they are going to be inside there following all this ordering, and hence for any set, your supremum and infimum exist. Okay, that's a bit of fun having this plus and minus infinity in this system. So in this case, they both exist. So that's the point. Now I define the heart of the matter of the measure theory. So suppose X is a non-empty set, and S is a subset of P of X. Okay, and what is P of X? You know that it's the power set of X. That means set of all subsets of X. We write this because so P of X is what? A. Yeah, I'm teaching such that. So just.
Yes.
No.
Okay. No, I thought you are. Yeah, sir. Please continue.
Okay, yeah. So it's just set of all a. I'm just writing in this way. Set of all subsets of A. Okay. So in particular, empty set is there, and full set X is also there, and so on so forth. Yeah. By the way, you have to tell me if I'm doing something wrong. Okay. If you don't agree, or because I do mistake, and quite often. So you have to stop me and correct me. And that's how I usually teach, by the way. Sometimes I do mistake intentionally or right, but then if you don't correct me, then that will be the case. Just hold on for a minute. This is the problem, you know. Just hold on for a minute. Teaching. Sorry about that. Okay. So you take a subset of the power set X. That means S is what? S is a collection of subsets of X. It could be P of X. It could be just the empty set also. Or it could be some finitely many subsets of X. Doesn't matter. Just a set. Okay. So we say that S, and here is a you are going to face different notation by different instructor perhaps. Some people call it A, and I think Rudin call it R, I guess. In a fashionable way, Rudin also call it that as R. Something like that. It doesn't matter. For our lecture, we'll stick to S. So we say that S is a sigma algebra if you have all these three properties. Number one, the empty set should be there. So we don't have to say that S is non-empty. There is already a set. Empty set is already there. Okay. Secondly, A in S would imply A complement is in S. That means you can say S is closed under complement. Third, if you take a sequence AN from S, n from 1 to infinity, then the union is also in S. So in other words, you say that your S is closed under countable union. So what are you saying? Number one, empty set must be there. S is closed under complement. That means if A is there, then A complement is there, and S is also closed under countable union. By the way, when I write A complement, since A is also subset of X by A complement, I mean X minus A. Okay. By definition. All right. Now here is a note. If 3 is valid, look at number 3. I have considered this as a countable union. If 3 is valid for finite collections, so instead of 1 to infinity, if I say an from n equals to 1 to L for some natural number L, this is closed. So if you say that it is closed under finite collection of finite union, instead of closed under countable union, closed under finite union, then you call X as a algebra. So what is the difference between algebra and sigma algebra? Algebra is closed. So 1 and 2 are there with algebra as well as sigma algebra. For algebra, number 3 is finite union. For sigma algebra, it is countable union. Okay, and because of countable, I think this notation sigma pops up. That's perhaps the reason it's countable sigma. So the definition, the definition is clear to you. Okay, fine. So a couple of observations. So suppose S is a sigma algebra. So a sigma algebra should be a subset of power set of X, and by definition it must be non-empty. So in that case, your X is also in S, right? Why? Because you said empty is there, so empty complement, which is X, must be there. Number one. Number two, it's a sigma algebra. Okay. Number two, if it is closed under countable union, so it is also in particular closed under finite union. Of course, it's easy because you take a finite union like this. You take finitely many ANs, A1 to AN, and then you define the AN plus K as empty set, right? And then you can invoke 3 to say that. In particular, sigma algebra is an algebra. It's very clear. You should think about an example, homework, that an algebra, there are algebras which are not sigma algebra. Okay, so other way it's not true. Number 3, what did I say here? I said S is closed under countable union. In number 3, I'm saying something else. I'm saying the same thing, but instead of union, I'm replacing it by intersection. So this is what I'm saying. So for all an in S, the intersection of an is also in S. That means it is also closed under countable intersection. You see why it is so. It is very simple. Set theory. The set theory goes as follows. Look at n equals to 1 to infinity an. You want to prove this belongs to your S, right? But you can write standard set theory, this as the union of n complement and then full complement, right? And if you look at this, look, your an belongs to S, so an complement belongs to S, right? By part 2. So an complement belongs to S. So maybe I show you. So this is a problem because I don't see your face. So I'm always nervous. You are getting it or you're not getting it. Okay. If you don't, if student doesn't get it, I don't feel good. You know, that's the problem. So if this belongs to S, then by part 3, this entire union also belongs to S. You agree? And if entire S, this belongs to S, then again the full complement is also going to belong to S. You agree? So this is how it goes. So all you have to prove this equality, and that's the homework. What is homework? That this equals to this. Lots of set theory, by the way, and lots of inverse function, etc. Inverse function is unavoidable because I told you in the very first lecture that that was Lebesgue's idea. He want to pull y-axis to x-axis. Okay, so a lot to do with the inverse function. Maybe not today, but tomorrow. Not tomorrow. Day after tomorrow, I'll talk about that. Is there any question on this equality? Is it fine? All right. Yeah. Okay. So number 4, this is the difference, right? So what is the word for this? A minus B. Let's say A minus B. So A minus B, which is defined. Okay, how it is defined? Maybe I write this down since I'm introducing first time. So those x in A such that x not in B. Okay, and as far as set goes, so this is your set A, this is your set B, and A minus B is going to be this region. So another way to say A minus B is A intersection B complement. Is it right? So if you accept in this from this point of this, if you accept this equality, and if your A and B belongs to S, if your A and B belongs to S, then A is so B complement is in S, and we just prove that it is closed under intersection, countable, so it is finite also. Same reasoning, right? And that would tell you A minus B is also in S. Now you understand we started with 3 assumptions, and all these natural things also holds true. Here are some examples. Suppose X is a non-empty set, and then S is a sigma algebra where number 1, S is full of Px. Any doubt? If S is full of Px, then certainly is sigma algebra. Or S equals to only the empty set and the full set, then it is also sigma algebra, right? And here is a little bizarre one. Number 2, take A subset of X such that either A or A complement is countable. That's going to be a sigma algebra, right? You see that? Of course, I said why it is sigma algebra, but you see that, right? And then in part 2, I have asked a question which just came to my mind is while I was preparing that suppose your X is full of R, the real line, and what is this? Oh, I said, so if you consider in this setting, suppose your X is R, would it imply, will that imply that your S, the way you defined, is going to be P of R? That's a question. Okay, I'm not assuring anything. So if your X equals to R in this case, and if you define S in this way, is it true that your S is going to be P of R? And that's a homework. Think about it. Okay. Another question, maybe it just came to my mind. So number 3 maybe. Suppose cardinality of, is it a good question? Okay, yeah, easy. Suppose the cardinality of x is finite, then s is what? Think about this. S is this is okay, the way it is defined for this part. Do you have a quick answer for this question? So if x is finite, then what will be x? S?
is equal to px.
It's going to be px, is it? Okay. Cool. Fine. You please cook up few examples, and also you can think another way to do it. Okay, another way to define it. It is just a little perturbation. So it says that instead of countable, you say that part B, you replace these by finite. Would it make any difference? You understand my point? You do part 2 with all these subsidiary questions, and then you come back to again this question, and you replace countable by finite. So either A is finite or A complement is finite, and you redo everything. What you get? That's my question. You understand the question? Do it by yourself, or ask in the tutorial. It's very easy, but do it by yourself. If you don't, if you have doubt, then please clarify. Okay, make it clear. You have no problem. Simple. Another way to, this is another simple example. So suppose x is a finite set 1, 2, 3, 4, and then you consider S as empty x 1, 2 set. Okay, because remember S is a subset of P of x, and if you take 1, 2, then its complement must be there, and the complement right here would be 3, 4. Okay, so this collection is going to be also a sigma algebra. These are simple examples, and you will see more examples. More we move on. And here is an example, another example, in fact, along this line. But this example is slightly different. It is the following. Suppose S alpha, where alpha ranges over an index set. So it may be countable, it may be uncountable, doesn't matter. So S alpha is just a collection of so this is a collection of sigma algebras on X. So X is a set, and you consider a collection of sigma algebras. Okay, call it S alpha. And what you do, then you consider the intersection of all the sigma algebras and call it S. Then I'm claiming that intersection is also going to be a sigma algebra. Okay. Now, when you say this is sigma algebra, first you make sure that empty set is there or not. Of course, since S alpha is a sigma algebra for each alpha, so empty set belongs to here for each alpha, and hence empty set is in this intersection. So empty set is in S, right? Similarly, X is also in S. Okay, you don't need this. But in any case, I think you don't need this X. Empty set is there is good enough. That would tell you at least this intersection is non-empty, because you need that to do any operation. You need to know that there is something. Otherwise, you will be in void situation, right? Then, so that tells you that empty set is in S. That's the first condition of the sigma algebra. Second condition is closed under complement. Well, you take A from S, right? So then A in S alpha for all alpha, that would imply A complement is in S alpha for all alpha, and that would imply A complement is also in the intersection. Similarly, S is closed under countable intersection. Do this homework. Okay, this is the homework. You should not accept it. Just because I'm saying you should not accept this. Or try to do it in the tutorial. Very easy, but make sure. So this example tells you what? If you have a collection of sigma algebra, then the intersection is also a sigma algebra, right? That gives a very interesting way to look at something different. So that's what I'm saying. The above example motivates the following. What is the following? So this is a very important definition. This is the following. It goes as follows. Suppose F is a set. Okay, so it's F is a set of what? It's a subset of P of X. Okay, that means F is a collection of subsets of X. That's the right way to say. Okay. Why is it that F is a subset of F is a subset? Okay, the sigma algebra generated by F, denoted by sigma F, is the intersection of all sigma algebras containing F. So you understand what I'm saying? So you start with the subset of Px. It is not sigma algebra, it may not be algebra, it may not be sigma algebra, it's just a subset of P of X. Start with any subset you wish. Then I'm saying the sigma algebra generated by F, which we denote by sigma of F, is the intersection of all sigma algebras containing F. What is the idea behind it? Well, the idea behind it is this one, simply, right? Why? So here's a theorem that I'm going to explain now. If F is a subset of Px, then sigma F, the sigma algebra generated by F, is intersection of all S which contains F, such that S is a sigma algebra. So sigma F is the intersection of all sigma algebras which contains your given F. That's the theorem. And what is the proof? One line, right? Why? First of all, you consider, you look at this collection, set of all A's which contains A, and A is sigma algebra. You call this as a set Z. And this collection is not empty because full Px lives there, because full Px satisfy all these conditions. And then you know that the collection Z is non-empty. And then you do what? Then you just apply this observation, you take the intersection, right? And this intersection is going to be the sigma algebra generated by that set F. You have to prove yet this is the...
Sir?
Yes?
So I have a query that we are defining sigma F to be the set intersection of all sigma algebras containing F. Then we are proving the same thing. So
then you have to prove?
Then we are proving the same thing in the theorem. So sigma...
No. Oh, you are right. That's where I got a little bit stuck and I did some stupidity, it looks like. Can I do the following? So I have to change this. You are right, and that's where I got a little confused that what I'm talking about. Then sigma F is the, so I cancel.
We want to define sigma F to be the smallest sigma.
Exactly, that's what I'm, so what is it? The smallest?
Smallest sigma algebra containing F.
Sigma algebra containing F, right?
Yes, sir.
Yeah. Now it is clear. And are you sure that we proved this? So what we proved the intersection is going to be a sigma algebra which contains F. And once you take the intersection, there cannot be anything smaller than that, right? Because if you take anything smaller than that, that will fall into that, right, in this class. And that's going to be, again, equal to the intersection. So is it clear? And thanks for correcting me. Now you see that I do mistake, right? Even I prepare all these things, notes, all these things well ahead of time, but I do mistake. Now is it okay, my friend? I don't know your name. No? Now is it okay?
Yes, sir. Yes, sir.
Okay. Okay to all of you? Right. So this was not correct. Fine. So what you are now guaranteed. So you can do the following. You can pick a subset of Px, your favorite subset of Px, And looking at that, you can produce a sigma algebra which is the smallest one containing that your favorite set. Okay, so this is what you can do, which is very nice. And here is an
Sir,
example. Yeah.
Can you once explain why was this wrong?
Oh, see, it was bad because look at the definition. The definition is what? F is a subset. Then the sigma algebra generated by F is the intersection of all sigma algebras containing F. That is the definition. Okay. This is the definition.
Yeah.
And then in the statement, what I wrote, say, suppose F is a subset of Px, then sigma of F, by definition, what? It is the intersection of all sigma algebra containing F. And that's exactly what I wrote in the right side. So I wrote the definition in the theorem, right? So what I wrote here is just the definition. So there is nothing to prove.
Okay.
But what is the statement? The statement is the following. Sigma F, which we call the smallest, the intersection of all sigma algebras containing F, is the smallest sigma algebra containing F.
Okay, sir.
Okay, and still it's not okay. Fine, yes. Here is an example of such thing. So suppose your F is just singletons, set of all singletons. Okay, is it a sigma algebra? No, right? Because you take the union of two singletons, it's not there. So F is not a sigma algebra, correct? But you can talk about the sigma algebra generated by F. Then what would be the answer? So sigma of F, sigma algebra generated by F, the singletons, is going to be this. All A subset of X such that either A or A complement is countable. And then I said, why? That's a homework.
Sir, can I comment on the earlier one?
Huh?
Earlier one, smallest sigma algebra.
Right.
So just one comment, sir.
Wait.
Yeah. So actually, how we need to prove it is a smallest sigma algebra. So what is that we need to prove? Ask that question to yourself. Then it becomes easy. First of all, you need to show it is a sigma algebra. Then you take any other sigma algebra, it is contained in that. If you prove that, then it becomes a smallest sigma algebra. That is what we need to show. Yes.
Right. Right. I agree. I mean, I goofed up a little bit here, but I hope it's clear to you guys. If it is not clear, reiterate again and ask in the tutorial or in the next lecture. I'll do it one more time. Okay. But the idea is simple. You start with a set A. Look, forget all this. So from the beginning. So you have a set F, subset of Px. First, ask yourself, is there a sigma algebra which contains your F? The answer is yes, Px itself, right? Once you are assured one of these guys, then you do what? Then you take all possible sigma algebras. Yes, you raised your hand. Is my mistake or what? No, I guess not. So then you look at all the sigma algebra which contains your F and take the intersection, and it is already guaranteed in this example, the intersection is going to be a sigma algebra. So you have one sigma algebra which contains your F, don't you? What is that? The one which is the intersection of all sigma algebra containing F. Clear? Now you ask, is it possible to find any smaller one who contains F again? Your answer is no, because you have considered all of them. That completes the proof. Proof of what? Whichever way you define it proves the other way. You say sigma of F is the smallest sigma algebra containing F. If that's your definition, then sigma F is the intersection of this class, whichever I erased would be your result. Or if you take this as your definition, you get that as a result. Is it clear? Right? It's not complicated at all. Is it clear to all of you?
Yes, sir.
As you said, you need to know what you want. You want a sigma algebra which contains your F and the smallest one. So you take this as a definition or that as a definition, the other one will be free. Why? Just because of this key observation. There is always, you can take the intersection, you're going to get the one. Once you take intersection, you get the smallest one, right? Simple. By the way, I told you I do sometimes mistake by intention. This was not by intention, okay? This I did, but I do this, okay? And I figured sometimes it helps you because it gives you some vibration, and I need that. Otherwise, it's very sleepy class.
Sir,
Yes, sir. Go ahead. Go ahead.
sir, why this word generated came here? I
Huh?
mean, why this word generated? What does mean here? Are we making a sigma, every element sigma f is by element of f?
Are
I
we?
mean, like in vector space, generated by means.
Oh, no. This has nothing to do with vector space. This has nothing to do with.
No. My question is that in sigma f, every.
Oh, this is the notation. This is just a a name. Sigma algebra generated by A. It's the definition.
Okay.
It's terminology.
My question is that let us consider that sigma f.
Okay.
Is the intersection of all sigma algebra containing f.
Okay.
So, what does it mean generated by? Are we making sigma every element of sigma f by?
Wait. Yeah. I maybe I try to help you. So you do the following. Suppose you take a subset. See, F is what? F is a subset of Px, right? Correct?
Yes, sir.
Now you ask, so I got F and I got P of X. Correct? This is a sigma algebra.
Yes, sir.
Now you ask, is there anything in between these two? Proper. Or maybe proper, let's say. Or it doesn't matter. Is there anything in between these two? Who? Another sigma algebra. You understand? You can ask this question, right?
Yes.
F is not a sigma algebra. If F is a sigma algebra, you don't ask this question. But if it is not, then you ask, is there a sigma algebra in between F and Px? What does it mean? A sigma algebra smaller than Px. Clear? Suppose you have an answer. Suppose yes, you say that I have a sigma algebra S1. Then you say, okay, is there anything again in between F and S1? Is there anything? Right?
Yes.
And then you say, okay, I have another S2 in between these. But then you ask, where do I stop? Okay?
Yes.
Where do you stop? Well, you take whatever you have, take the intersection, and that's where you stop. That's the reason the smallest one will be, we will call it as generated by F.
Okay.
Did I answer your question?
Yes. Thank you.
Right? So what is the point? The point is to get someone in between F and Px, whom, well, not arbitrary guy, someone which is sigma algebra, but must be smaller, right?
Yes.
As small as possible. But you cannot take empty. Why? Because, well, you must have the assumption that F should be contained in that sigma algebra, right? Now, since you mentioned about vector space, suppose you look at R3. Now I'm going to take 5 minutes extra because I have to complete this. Suppose you look at R3, okay, and you remember that standard basis E1, E2, E3, right? Now suppose I ask you, give me a vector space, subspace, which is generated by E1 and E2, or let's say only E1. What would be your answer? Your answer would be this is E1, E2, or E1, E2, E3. Right? That means this is full R3, this is R2 with X, Y axis, etc. Right? But if I tell you what will be the smallest one, well, this one will be the smallest one. But if I just say, the vector E1, then you will say it is just the X axis. That would be your answer. It is just along that line. Right? Clear?
Yes, sir.
Wonderful. Now I come back this example. So this example, you please do. What is the example? It's the following. So you look at F, all singletons, that is your F, and then you ask, what is the sigma algebra generated by F? That means, in other way, tell me the intersection of all sigma algebra which contains F. the answer would be, I hope, would be all those A subset of X such that either A or A complement is countable. Remember, we talked about this earlier, right? So this is going to be your answer.
Sir,
Yes.
if crypt F is the set of all singleton sets.
Yes. Yes.
So F is subset of sigma F. If
Yeah. Okay. Okay. Are you asking whether F is subset of sigma F or not?
yes, sir.
That's a good question.
Then X singleton set X complement, that is X minus X is a is an element of sigma F also. That is X.
So can I throw an assumption that X is a countable set?
If sigma F is the smallest sigma algebra containing F, then X is countable. This implies that X is countable now.
That's what I'm saying. So can I assume that X is countable itself? So I'm assuming that X itself is countable set.
Yes, I have to assume X.
So you are saying you have to assume X is countable, right? Let's do that. Let's do that. And if it is not countable, then what? That would be also a question. And what if? And
if it is not countable, then sigma F is elements of sigma F are phi.
Sigma F
Phi
is
also. Phi? No, phi.
It cannot be phi, right?
Sorry, sigma F is empty.
It can't be empty, right? It can't be empty, right? Because sigma F must contain singletons. It can't be empty. You can ask, is it going to be P of X? There is one guy always, right? P of X, right?
Oh, yeah.
Is it right? So these are all questions, man. I didn't thought about all these so details. Please think about this. But I thank to you for your question. It's a very good question. Do you understand? The rest of you understand what she asked? It's a very legitimate question. So it seems I have to assume this is countable. So I do that. And with this assumption, can you prove this equality? So with this assumption, can you prove this equality? And that is the reason I think I said why. Now I don't remember. Maybe I knew it, I don't remember. And then I asked, what if X is uncountable? That also you have to think. It is another case. What if X is countable but finitely minimal? Okay, that also. Can I take 3-4 minutes more?
Yes,
I need to.
Please go ahead.
I want to at least complete this slide. Otherwise, it's not good. Okay, so now I have a definition which I figured very recently. I didn't do quite well. So you know topological space, right? A topological space is denoted typically by x comma tau. What is tau? Can you help me? What is tau? So if you have a topological space which you denote by x comma tau, what is the meaning of tau?
Set of all open sets.
Right. Is it right or wrong? You said yes, then
the set of the topology, the set of all open sets.
Set of all open sets, right?
Yes, sir.
So this I have done something a bit of too much, unnecessary. So let X be a topological space. Then I want to say, remember, recall. Tau is that what you said. Those A such that A is opening X, right? Okay. And so this was a mistake again. So definition, the Borel sigma algebra of a topological space X is the sigma algebra generated by tau. So what is Borel sigma algebra? The Borel sigma algebra is the sigma algebra which is generated by open subsets of X, the topological space X, okay? And the elements of B are called Borel subsets. Now, here are a couple of remarks. Now, here I got tau. I don't know why I did this mistake. I have to take 3-4 minutes more. I'll stop at 40 because okay. So remark, C is in B for all closed subset, right? Because a set is in B, then complement is there. So all the closed sets are in the Borel subset, the Borel sigma algebra, which is very different from tau. Tau doesn't contain closed sets, right? Countable union of closed sets, which you call F sigma set, they are also there, right? And countable intersection of open sets, by definition, these are known as G delta set, they are also there. So B is closed under countable union of closed sets, countable intersection of open sets, which is very different, right? So it's much larger Borel sigma algebra. An interval AB is rational definition if the endpoints are rational. So here is a standard claim. Suppose U is a subset of R, which is an open subset. With respect to usual metric or topology, then there exists a countable rational intervals. That means intervals with endpoint rationals, which will cover your open set U. And I leave this proof. It's very standard, and I am sure you know this. It's one line essentially. So indeed, if you take X from U, for each X, you are going to find an interval which is rational interval, endpoints rational, right? And then you cover it, this U is going to be covered by IX, but Q is countable, and then this union must be countable. So you can always do that. That tells you, so if U is the union of J, so U is the union of J, an open set U in R, and J and R rational intervals, then you do what? You set F to be the set of all intervals AB, where ABs are rational, that means set of all rational intervals. Then you know that sigma F, the sigma algebra generated by this guy, will contain the sigma of tau U. What is tau U? Tau U is the usual topology on R. That means all the open intervals it generates, right? And so this is what it says because of this property, right? And this is of course always true. And then you prove what it proves, that your Borel sigma algebra generated by this usual topology on R, which you call B here, is nothing but sigma of AB, where ABs are all rational. So the Borel sigma algebra with respect to the usual metric, the Borel sigma algebra, come on, this I can't do anymore. There's a problem here with this pen. So the Borel sigma algebra generated by this usual topology on R is going to be also the sigma algebra, the smallest sigma algebra generated by this open interval AB with endpoints rational. So this also gives you a hope, if you know this equality. If you are not very sure, ask in the tutorial, that this Borel sigma algebra also for the usual topology in the real line is also the sigma algebra generated by minus infinity to A closed, where A is rational, or closed A infinity, where A is rational, or AB closed, where ABs are rational, etc. All these things will give you the same Borel sigma algebra of the real line with respect to the usual topology. And that's where I stop. Sorry about this extra time. You have any quick? Yeah, this is a homework which is very easy. The homework is the N version of Rn. So you look at Rnu, and instead of this, then you're going to talk about the box. So box is this product of all open intervals AI BI, and you again prove the same set of result. And this is a bit of homework you can try to do. Now I stop. Sorry about this. So you have any quick question, because the next lecture is 5